Shruti.
Hi, everybody. Thank you, Barbara, for the introduction. I'm really excited to be here and talk about these bias noise cat-qubits with all of you. Some of you may have seen this talk before, but please wait. I have new results, hot and new results that we just got in the last few days. So that'll be interesting. Okay, so there are two main messages that I would like for you to take away from this talk. Firstly, know your noise. Know the structure of the noise. People usually just quote fidelities. And I think that fidelities should not be the only metric to define how good your gates are. As you will see from this talk, the structure of the noise is equally important. For the same fidelity, one gate can be, but for the same fidelity of the gate, if the structure of the noise is different, you can get better performances. The second message is, in order to have a scalable, fault-tolerant quantum computing, it's important to actively suppress the noise at the physical level as much as you can before you start scaling up. And this is sort of the whole idea behind bosonic qubits, is that you perform some local error correction to reduce errors in the qubit themselves, and then you can concatenate it with other codes to correct for whatever errors are remaining. In that flavor, today I'll be talking about the pumped nonlinear cat-qubits, in which you obtain this inherent error correction against phase noise just because you are pumping your system in an interesting manner. Okay, so with that, I'll give you the outline of my talk. So firstly, I'll introduce what bias noise is, and then I'll introduce surface codes that are tailored to bias noise. Then I'll introduce this bosonic cat-qubit, which is a qubit which has bias noise, and I'll give you an intuition to understand where this bias comes from. I will also tell you about the different qubit operations that we can do. And then I will tell you about how you can use a very interesting gate, and this technique we sometimes call as cat hack, and how you can use this to make the surface code performance really good. And finally, I will tell you some of the new results about fault-tolerant thresholds, which we obtained for this XZZX surface code. Many people will not be familiar with this XZZX surface code. It's something that was not developed by me. It's developed by these guys in Sydney. And David Taquet is actually going to talk about it this tomorrow. So please see his talk at 9 a.m. tomorrow. But I will show you some of the work that we did on this XZZ surface code and the fault-tolerant thresholds for this surface code. Okay, so let's, so let's look at the first part. So typically when we talk about quantum errors, we decompose that into three types of errors. The bit flip error, which is just like the action of the X operator on your qubit. So it just flips 0 to 1 and 1 to 0. Then you have the phase flip error, which is the action of poly Z operator on your state. So it just messes up the phase information. And the poly Y error, which not only flips the state of your qubit, but also messes up the phase information. The most common error channel that people study are depolarizing channels, where we say that the probability of all these three errors is the same. So the probability of the Z error is same as probability of X error and the same as probability of Y error. However, there are many systems where the qubit couples to the environment, preferably along one axis of the Bloch sphere. And in that case, we get that the noise along that axis is more dominant compared to the other types of noise. So such qubits are called as bias noise qubits. And in this talk, we will look at a particular bias noise qubit in which the probability of Z error is more likely than the probability of X and Y error. For this qubit, the coupling to the environment is predominantly along the Z axis of the Bloch sphere. So in this qubit, the phase flips are dominant while other errors are suppressed. We will also define a bias which is the ratio of the probability of a Z error and the sum of the probability of X and Y error. So if there's only pure Z noise, then the bias is infinity. And for depolarizing noise, bias is half. Okay. So now let's look at the surface code. So this is sort of our general, the regular surface code in which you have the qubits on the 2D lattice, and you have two types of stabilizers. The 4-body X stabilizer, which is the four-body X operators acting on the 4 qubits around the blue plaquettes. And then you have the four-body Y stabilizer, which is the four-body Y operators acting around the qubits around the green plaquette. Now, you must have seen the surface code with the X and Z stabilizers rather than the X and Y stabilizers, but it doesn't matter. It's just, it is done for a particular reason in this talk, but you can just think of this as the rotation of your Bloch sphere by 90 degrees. Okay, so now how do you measure these stabilizers to detect for errors? What you do is you put an ancilla at the center of the plaquette, and then you perform these C0 gates between your data qubits and the ancilla qubits, and then you measure the ancilla. So if the ancilla was measured to be in the same state as it was initialized in, there was no error, but it flipped. But if it flips, then there was an error in one of the data qubits. Okay, so it turns out that you can, if the data qubits have bias noise, that is the probability of Z error is more likely than the probability of X errors and Y errors, then the performance of the surface code can be improved. You can, the threshold for the surface code, for this surface code with these stabilizers increases for the Z bias noise. And this was done, the work done by the Sydney group, and Steve Fleming is one of the authors and is at the talk here. Okay, so I'm just going to show you some plots from their paper. So this first plot shows the code threshold for the surface code against bias noise errors. So the x-axis shows the bias and the y-axis shows the threshold. And here there's errors only on your data qubits, but this syndrome extraction circuit is perfect. So as you see that as the bias increases, the threshold increases, and when there's infinite bias, so only pure Z errors, then the threshold becomes 50%, which is close to, which is the threshold for the repetition code. And in fact, in that case, the surface code essentially reduces to a repetition code. And if you look at the bias of half, which is depolarizing noise, the threshold is about 20%. But you see that even for a bias of 100, you get a factor of 2 improvement in the threshold. The figure on the right here shows the threshold under phenomenological noise model, in which we take into account the measurement errors that some of the syndrome measurements could give a wrong result. In that case, of course, the threshold decreases, but you still see that the threshold does increase as the bias increases. And even for a bias of 100, you still get about a 5% threshold. And this is, again, close to a factor of 2 improvement compared to when it was depolarizing noise. So you do get this improvement in the threshold, which is amazing. Like having a threshold of 5% is pretty awesome.
Shruti, can I ask a brief question?
Yeah.
The measurement error rate is the same as the dephasing rate? Is that
yes,
correct?
That's
it's
right.
The high error rate. Okay,
yeah.
Thank you.
Yeah, that's right. Okay, so now the group at Sydney also developed this XZZ surface code, which also works for bias noise qubits. And in this case, all the stabilizers are actually the same, but they're mixed in the sense each stabilizer has 2 X's and 2 Z's. And in this case, what you do is, in order to measure the stabilizers, you will do 2 C0 gates and 2 C phase gates between your data qubits and the ancilla qubits. And you will see very shortly that this has an advantage because if you think about circuit level noise in these bias noise qubits, the CZ gates is easier to do than the control NOT gates. And so having fewer control NOTs is an advantage. Okay, and again, David is going to talk about this XZZ surface code tomorrow. And their paper is in preparation. Now what we would like to think about is, does the improvement in the thresholds survive if we take the circuit level noise model into account? Basically what can happen is that these gates are faulty, and the gates not only propagate the errors, but the gates can actually change the nature of errors. So say your dominant error was a Z error. If you try to do a gate which doesn't commute with a Z, then that gate will convert a Z error to an X or Y error, and that will tend to depolarize the noise channel. And this can reduce the improvement in thresholds we would have otherwise expected. To understand this point a little bit better, let's look at how you would measure the stabilizers for the XZZX surface code. So when you were doing the control Z gates, then what you would do is you would engineer a ZZ type interaction between your ancilla qubit, the ancilla qubit and the data qubit. Now we're looking at bias noise qubits in which Z errors are dominant. So if there's a Z error on the data qubit during the gate, the Z just propagates through the interaction, and a Z error on the data qubits propagates as a Z error on the data qubit itself, no big deal. And similarly, if there's a Z error on the ancilla qubit, it propagates through. And so the noise channel of the CZ gate is biased. The other things, the other elements of this measurement circuit is the preparation of the ancilla and the measurement of the ancilla. Again, these errors are trivially biased. You are preparing and measuring the ancilla along the x-axis. So either it's either in the plus state or the minus state. And a Z error will only take plus to minus and minus to plus. So that's it. The errors in preparation measurements are trivially biased, just like the CZ gate. Now, what happens with the C0 gate? In this case, you will engineer some sort of XZ type interaction between your data qubits and the ancilla qubits. Now, if there's a Z error in the data qubit, then this doesn't commute with this Hamiltonian, and it will actually propagate as a linear combination of Z errors and Y errors on the data qubits. So the CX gate basically unbiases or depolarizes the noise channel because it's converting the dominant error Z to the less dominant error Y. And this is not good. In fact, there's a theorem that native bias preserving C0 gates between physical qubits, which have bias noise error channels, is actually not possible. And let me now quantitatively give you an example of why it is important to have this bias preserving, why it is important to have a C0 gate which preserves the bias. So what we do is we take the XZZX surface code, we take the decoder that these guys developed at Sydney, and we look at the logical error rate versus the infidelity in the CX and CZ gate. So we're doing like a full circuit level noise simulation. But here, just as a cartoon model, we're assuming that the CX gate is biased. Suppose this was the only type of errors that could happen. And we assume that the CX gate and the fidelity of the CZ gate is similar. And we assume that the initialization and measurement errors is half the gate infidelity. So with this sort of simple cartoon model, we look at the logical error rates for different sizes of the surface code, and we get these plots here. And clearly we get this threshold effect of about 2%. Great. Now what we do is we take the real error channel of the CX, which is not going to be biased. It is going to have Y errors. And clearly now you see that the threshold has decreased. It was about 2% here, and it's about 1.6% here. More importantly, you see that for the same gate infidelities, the overall logical error rates are lower if I have biased CX gates versus if I don't have those gates. So if you look at, for example, this point here, the logical error rate is about 10 to the minus 4, whereas in this case, the logical error rate is about more than a factor of 10 larger. So this example clearly shows you that there is an advantage to having bias noise gates as well. If you don't have them, you will not get as big as an improvement that you would have otherwise expected. Okay, so now I will tell you about this cat-qubit and how we can make a bias-preserving C0 gate with these cat-qubits. The bias-preserving C0 gate is based on the phase-space topology of the cat states, and it's not dependent, and you cannot replicate this trick with just regular, strictly two-level systems, and this is sort of unique to bosonic systems, higher-dimensional bosonic systems. Okay. So with this, we come to the second part of the talk. Let's look at this bosonic cat-qubit, which is realized by driving a nonlinear oscillator. So firstly, what is a bosonic qubit? A qubit encoded in two orthogonal states of an oscillator or bosonic form a qubit. Typically, these bosonic qubits are made in harmonic oscillators. So A and A daggers are the annihilation and creation operator of your bosonic modes, and omega is the frequency. So why do we want to make a bosonic qubit? Because, well, the lifetime of typically the lifetime of the oscillators are larger than the lifetime of the qubit themselves. This is especially true in superconducting circuits. The lifetime of your microwave cavities can be several orders of magnitude larger than the lifetime of a transmon qubit, for example. Also, you can do some local error correction on this. So this is, for example, the concept behind GKP codes, for example. The problem, though, is that you cannot control the state of a qubit in a harmonic mode. You need some anharmonicity to be able to perform operations. So you need some external nonlinear medium. For example, in superconducting circuits, this could be your transmon qubit. You need that nonlinear element to actually do anything to even prepare these qubit states in your harmonic oscillator. What the problem then happens is that you are limited by the lifetimes, by the noise properties of this external nonlinear element, because when these two guys interact, the bad properties, the noise properties of this nonlinear element are actually backpropagated onto your harmonic mode, and so the system is in some sense not fault tolerant. So you basically inherit all the properties, all the bad properties of the nonlinear element itself. So it's not great, and this limits the performance of many bosonic qubits. One thing that can happen, for example, is that this nonlinear element can introduce nonlinearity into this mode, which can be bad. So, for example, it can, in the superconducting type of circuit, it can introduce what is called as a Kerr nonlinearity, and that is a bug for most bosonic qubits. If you take binomial qubit, binomial codes or GKP codes, the Kerr nonlinearity is bad. So the question that we asked ourselves a few years back was, well, can we use this Kerr nonlinearity as a feature and not as a bug? And that is indeed what we did with these cat-qubits, driven cat-qubits. We're going to use this Kerr nonlinearity as a feature. We're going to drive this Kerr nonlinear oscillator in an interesting way to create a protected cat state. Okay, so now we have to look into some quantum optics. So just as an introduction, let's look at what coherent states are. The coherent states are the eigenstates of the photon annihilation operator. So coherent state alpha is an eigenstate with eigenvalue alpha, and coherent state minus alpha is an eigenstate with eigenvalue minus alpha. You can represent these states in the phase space. So the x-axis here is like the position, and the y-axis here is like the momentum. And in the phase space, the coherent state alpha looks like a blob at plus alpha, and the coherent state minus alpha looks like a blob at minus alpha. So here, in this example, I'm imagining alpha to be real. So the imaginary part of alpha is 0, and therefore this blob is along the q equal to 0 axis. Okay, so now let's look at cat states. Cat states are the superposition of these two coherent states. The Wigner functions of the cat states look like this. So if you have an even superposition cat states, alpha plus minus alpha, then you'll have two blobs, one at minus alpha, the other at plus alpha, but then you'll get these interference fringes at the center to show that it's a superposition state. And similarly, for the other superposition state, you get this interference fringes at the center. Importantly, for the even superposition state, the interference fringe at the center is positive, whereas for the odd superposition state, it is negative. And that's how you can identify whether you have a even superposition state or the odd superposition state. You can also look at the photon number distribution for these cat states. So the even superposition state has only even photon number states occupied, and it's called as the even parity state. And the odd superposition state has only odd photon number states occupied, and it's called the odd parity state. And from now on, I'll use these cartoon images to show the Wigner functions. Okay, so now, obviously the even parity state is exactly orthogonal to the odd parity state, and I can encode a qubit in these cat states. Okay, so how do we make these cat states in a nonlinear oscillator? before understanding that, let's look at our nonlinear oscillator. So I'm going to give you an example of this nonlinear oscillator in superconducting circuits. So we have a superconducting Josephson junction, and its Hamiltonian can be approximated by this formula here. So the first term is a frequency term, the second term is a nonlinearity. The eigenstates of this Hamiltonian are actually the Fock states. So I'm showing the eigenstates in the rotating frame. So I go in a frame where this first term disappears. And in this rotating frame, the Fock state 0 and Fock state 1 are the degenerate eigenstates. And then you have Fock state 2 and Fock state 3 and more of them. They have lower energy compared to the Fock state 0 and Fock state 1. And this might seem weird to you, but this is just a feature of the fact that I'm in the rotating frame. That's all. There's nothing like wrong about it. Okay, so now the Fock states are separated from the Fock states 2 and higher are separated from the 0 and 1 states by an energy gap. And so you can use the 0 and 1 states to encode a qubit. Now, if you do a spectroscopy of this transmon or this junction, you will see that if you apply a drive at omega q, if you apply a drive at this frequency, then you will cause transitions between 0 and 1. But if you want to go to another frequency, if you want to go from say 1 to 2, then you'll have to apply a drive at a smaller frequency. And this is the meaning of this negative sort of energies, that you just now need to apply a drive with frequency omega q minus omega gap to go from this guy to that guy. Okay, so these are the Wigner functions of the Fock state 0 and 1. This is the Fock state 0, this is the Wigner function of the Fock state 1. And this is exactly what the transmon states that we use for quantum computing, that IBM uses, Google uses, that everybody uses. Now what I'm going to do is I'm going to apply 2 drives to this system, which are equally red and blue detuned from the center frequency. In this case, what will happen is that because of this nonlinearity, we can take 1 photon from this drive, 1 photon from this drive, and convert it to 2 photons at omega q. As a result, you get this 2 photon drives, which means that you're exchanging 2 photons at a time with your drives. Omega q is just the frequency, and the phase phi is the phase of the drive with respect to some clock phase sitting in your system. Now, there's actually a simpler way to generate this Hamiltonian using something called as a snail, and the first cat experiment was actually done in this snail device at Yale, and that is why I'm showing it here. The snail has both 3-wave and 4-wave mixing capabilities. That is, it has this nonlinearity and also another third order nonlinearity, because of which if I can just apply 1 drive at 2 omega q to get this drive over here. Okay, so once we get this Hamiltonian, I can go into the rotating frame. That is, I get rid of these frequency terms from here. And this is a time-independent Hamiltonian that I get here. Now I can immediately factorize this Hamiltonian. This is an exact factorization, and write it in this form. I'm going to make a substitution. I'm going to call square root of these guys over here as alpha. So this Hamiltonian becomes like so. And now you'll immediately see that there'll be, So now you'll immediately see that there'll be 2 coherent states, plus and minus alpha, which will be destroyed by this term. And these 2 coherent states will be the degenerate eigenstates of the Hamiltonian. That means that they're even and odd superposition states, which are the cat states, are also the degenerate eigenstates of the Hamiltonian. So lo and behold, we have created a Hamiltonian whose eigenstates are the cat states. Now, if the phase 5 is 0, so say, I have a clock phase, and if my drive is in phase with that clock, then I'll say that the cats are formed along the position axis or the I-axis, and they're along horizontally oriented in the phase space. And if I just change the phase of the drive to say pi over 2, then because of the square root factor here, the cats will be rotated in phase space by an angle of pi over 4. So basically, I can just change the phase of the drive and get a different cat every time. And so each oscillator actually can hold infinitely many cat qubits. And this is what I will use to actually do the bias preserving C0 gates. But for now, forget about this phase. I will define my cat qubits with the phase phi equal to 0. That means they're along horizontally oriented in the phase space. So this is a block sphere that I will be using. My cat states will be along the X states, C plus and C minus. The superposition of these cat states, which are approximately the coherent states, will be along the Z axis, and then you have the other superposition state. So in this block sphere, the Pauli Z operator is going to take C minus to C plus and C plus to C minus, and the Pauli X operator just puts a phase between the C plus and C minus states. On the right-hand side here, I'm showing the eigenspectrum of this system in the rotating frame. Again, I have the C plus and C minus states, which are the degenerate eigenstates, and they're separated from the rest of the Hilbert space by an energy gap. And this energy gap increases with the size of the cat that you make. The more photons you put in, the bigger this gap is, and this actually allows you to do faster gate operations. So if you actually, it also turns out that as you pump the system, you get pairs of degenerate excited states. So there'll be these two pairs of excited states will be degenerate with each other. These two pairs will be degenerate, well, they will be quasi-degenerate, that is their energy gap is exponentially small in alpha. So if you do a spectroscopy in this case, you will see that the spectroscopy compared to the transpon has changed. You still get one line corresponding to the C plus C minus transitions, but now the higher excited, the excitations to the other states, the lines for the excitation to the other states start overlapping with each other, which tell you that these states have become degenerate. So this gap allows how fast you can do the operations. The larger the gap, the faster you can do the gates and better your fidelities would be. So in superconducting circuits, this gap can be made as large as 10 to 200 megahertz, which is about 100, which allows you to do gates which are 100 to 1,000 times faster than the typical decoherence time. So you can get really high fidelity gates. Okay, and just as an aside, there are about alpha squared by 4 pairs of quasi-degenerate states. And this is actually what gives you protection against phase noise. And this will become clear in a few slides. So how do you prepare these cat states? So what you do is you first start with an empty cavity. So there's no drive, and say your cavity is in vacuum. And now you slowly increase the drive from 0 to some constant value. Then the cavity, the oscillator will follow this drive, and if you initialize your oscillator to the Fox state 1, it will follow the drive, split to the cat state C plus. And if you had initialized your oscillator to the Fox state 1, then it will follow the drive, split to form the cat minus state. So this Hamiltonian preserves parity. So the Fox state 0 goes to C plus state, and Fox state 1 goes to the C minus state. I'm very happy to say that our theory results were confirmed in experiments recently, and this is the experimental realization of cat states. This experiment was done in Michel Davere's lab at Yale by two amazing experimentalists, Alex, Krim, and Nick. And this is the snail device in a copper cavity, and this is where the cat actually lives. And they were able to prepare, so the nonlinearity in the circuit was about 13 megahertz, and they were able to prepare the cat states in about 320 nanoseconds. The decoherence time was about 15 microseconds, so the initialization time is much faster than the decoherence time, so we're all good. Okay. So now I just don't want to prepare cats, I want to do some gates on them. So the one thing you can do is apply a single photon drive, and you see that if you just apply A to the C plus and C minus states, it's just going to flip the parity. And if you apply A dagger to the C plus or C minus states, it's going to flip the parity, but it can also take you to one of the excited states. But you see, if the frequency of the drive is at omega q, then you won't be able to go to one of these excited states because those excited states are at a different frequency. So those transitions are not allowed. And as a result, you can basically just write, project A dagger and A in the cat basis. And you see that A dagger looks like this, some weird factor times sigma Z, some other weird factors times Y, and similarly for A. This weird factor actually approaches 1 when alpha becomes large, and this factor becomes exponentially small when alpha becomes large. So if you have A dagger plus A, that becomes a sigma poly Z. If you have A dagger minus A, it becomes poly Y, but an exponentially small poly Y. So now you can immediately see that this is going to be like a bias noise qubit because it couples to the environment mostly along Z axis, and the coupling to the other axis is suppressed. So you can use this intuition to do Z and ZZ gates. So if you just apply a single photon drive, then you can do a Z gate. The duration for the gate increases, the time required to do the gate actually decreases. So the size of the cat, the bigger the cat, the faster you can do the gate operations. And similarly, if you couple 2 such nonlinear cavities, then you can do, this is just a simple beam splitter coupling, which can be easily realized in superconducting circuits. And this allows you to do a Z1, Z2 gate. Again, these gates can be very fast. In the experiment, they have been able to do a Z gate in about 24 nanoseconds. And compare this to the lifetime of 20 microseconds. It's amazing. Okay, so now I've talked about how I can control how the user can control the system.
Shruti, can I interrupt for a moment? Yeah, keep an eye on the time because I don't know how many slides you still have. So the
yeah, I'll be okay.
Yeah.
Right. So very quickly, I want to tell you about coupling to the environment. So you can write a general coupling to the environment like this. Now, what I want to show you, motivate to you, is that a Z, the coupling to the environment is going to be along Z. That is, it can flip C minus to C plus, but there won't be anything like an X coupling, which puts a phase between the C plus and C minus states. To see this, you can just project this coupling to the environment within the C plus and C minus bases. And if you do that, you'll see that this term can couple C plus to C minus, and this matrix element becomes polynomially large with the size of the cat. So A dagger MAN is equivalent to like a sigma Z operator. Now, okay, so now I've told you that it can couple to the environment, and the coupling to the environment is along the Z axis, and the strength increases polynomially with alpha. But what happens to the other axis of coupling? What happens to X? In order to understand that the coupling to the X axis is going to be suppressed, let's look at the classical potential corresponding to this Hamiltonian. So the classical potential corresponding to this Hamiltonian is actually a double well structure, and you have the 2 states, the coherent states minus alpha and plus alpha, sitting at the bottom of these 2 wells. Of course, quantum mechanically, we're going to have superpositions of these 2 states, which are our cat states. Now, in order for an X type of error, you have to go from minus alpha to plus alpha or plus alpha to minus alpha. How can you do it? Well, you cannot tunnel under the barrier. Tunneling under the barrier is exponentially suppressed. The other thing you can do is hop over the barrier. But in order to hop over the barrier, you need very high order coupling, which is also suppressed. So you see that you see that an X error is going to be very, very difficult to do. Now you can have low order errors, like just a single photon absorption, which can actually take you, it doesn't take you over the barrier, but it can take you to the next level, which is like causing a leakage. But any photon dissipation event will actually bring you back down. So you basically are never able to hop over the barrier and go from one side of the well to the other, and your X errors and Y errors are suppressed. So in fact, we have done more detailed analysis and shown in our paper that indeed this is a bias noise qubit, and the bias increases exponentially with the size of the cat. In a reasonable experimental setup, with reasonable experimental parameters, you can get biases as large as 1,000 for moderately sized cats with photon numbers of 5. In the current experiment, the bias is about 50, but this is just for very small size cats. We haven't reached the threshold for the exponential. We haven't reached alpha square of 5 yet. We are just at alpha square of 3. Okay, and this is true for all orientations of the cats, whether you're along the x-axis or any rotated axis, it doesn't matter. So here are the different operations that we can do in the system. I'm not going into the details, but I want to tell you that we can do all the operations that we want, and some of these have been demonstrated in the experiment. But now I want to go to the CX gate and tell you more about that. So I have, how many more minutes?
Well, we are now at 17:17. So in principle, we had 3 minutes. I don't know whether we started a little later. You are a bit
I can
short
just skip over to the main result then.
We started about 2 minutes late, I think.
How many minutes late, Steve?
About 2 minutes late.
Yeah. So 22 should this next talk start, but it would be nice to have some questions. So maybe you should pick what you want to.
Yeah, so let me just show the good part. So believe me when I say that there is a biasnoid CX gate that we can do, and it has this complicated Hamiltonian, and I was going to tell you how you can do it, but just forget about it. You can read the paper. Let me just quickly tell you the numerical results. Okay, so now what I want to do is go back to that XZZX surface code and simulate it for the real circuit level noise for these for these cat qubits and see what thresholds I get. So I basically assume faulty CX gates, CZ gates, add measurement errors, initialization errors, and actually simulate the master equations for these processes under most common sources of decoherence, which is photon loss and thermal photon gain. And from these master equation simulations, I extract the error channel and then look at the performance of this XZZX surface code. So here, so in this setup, the most difficult gate is the CX gate. That has the highest infidelity. So on the x-axis here, I'm showing you the infidelity of the CX gate. The y-axis is the logical error rate. The bottom x-axis is something for the experimentalist. It is the ratio of the photon loss rate to the nonlinearity. It tells you what sort of oscillator parameters or transmon parameters you're trying to hit to achieve that threshold. So if you look at this plot, so this plot is for one photon cat state. This corresponds to a single qubit bias of about 100. In this case, you can get thresholds as high as about 0.0, about like close to 3% thresholds. CX gate, so this is a threshold for the CX gate, which is, as I said, the most faulty gate. So this is nice. So what does this mean for the experimentalist? It means that if you have a nonlinearity of about 10 megahertz, which is close to what we have in our lab right now, then the T1 time of your system should be about 132 microseconds. So this is not too hard to do. This is a pretty reasonable number. In the current experiment, the T1 time is about 15 microseconds, not too far away. But now I increase the bias. I make a bigger cat, 6-photon cat state, which has a bias of about greater than 1,000. In this case, you see the threshold, it becomes close to 6%. So that's pretty awesome. And in this case, that would mean that I need T1 time of about 64 microseconds, much closer to what we have in the experiment right now. So my point is that now we truly have something reasonable we can do in the experiment, get these high fidelity, get these bias preserving gates and actually demonstrate some advantages in error correction. So this was sort of the main result that I wanted to show here. So this is just the last slide on, sort of the conclusions and perspective that this is a very scalable architecture. We can build this, and the experimentalists in the lab currently have a chip with 2 cat qubits, and they are doing the C0 gate on it. So hopefully in a year you will see this gate. And I will leave with the acknowledgement slide. And thank all our theory collaborators and the experimental guys. And I recently started my group in Yale, so I have postdoctoral positions open. If you're interested in working with me, please write to me. Thank you.
Okay, thank you very much, Shruti, for a very nice talk. People can clap, you know, well, people can't clap really, yeah. Okay, anyhow, nice talk. Of course, there are many questions, so let me just quickly insert one, go few slides back, just to understand these results. So you are setting sort of the control X. So you're saying I put all the other sources of error, I put them like the measurement error, the preparation error, I'm fixing them, right? And I'm just varying then the control X error.
No, I'm varying everything. So for every point here, I simulate the CX gate, the CZ gate, the measurement, and the initialization.
Right, but what are you putting in for the measurement error, right? You're not
measurement again. It's so we have a way to do the measurements. I simulate that whole protocol with these cavity parameters.
Right, but okay, but I guess in the paper that will come up, we'll see what the actual measurement error rate is.
Right. So in this case, the measurement error was about. So around this point, the measurement error was about 2%. So it was smaller than the CX gate infidelity, so I didn't show it here. For this guy, the measurement error was about 1%. The reason measurement error is smaller for n equal to 6 is because the way the measurement scheme is set up, it does better for a larger photon cat state. So the measurements also get better.
Okay. And of course, this doesn't yet include leakage, but you think that that's...
No, this includes leakage.
Includes leakage in the simulation that you...
Well, so what we do is for these cats, there's some leakage because of thermal noise. We put in an extra step to autonomously correct for leakage using our dissipative process. So there's another, in these simulations, there's another step where I'm just doing local correction for leakage.
Okay, but you can also, of course, quantify how much leakage, what the leakage error rate is. And
right, so for this, there was about 10 to the minus 6.
Oh, I see, that's very small.
Yeah.
Okay.
All right, Shruti, can I follow up on Barbara's question about the measurement error rate?
Yeah.
So that measurement error rate that you quoted must be somehow conflated with the gate error rates, or maybe I'm misunderstanding something. Because you said it changes depending on, oh, I see, because you're also plotting with respect to kappa and k?
Yes.
I see. Okay,
yeah,
I see.
Yeah.
Okay. I answered my own question.
Other questions? Of course, like you're saying, the C0 has not been done, so it'll be exciting to see how well this... I heard some noise. Who wants to ask a question?
That was me, Barbara. So I was going to ask, what's the CZ error rate here? Is it insignificant compared to CX?
So CX is about, so in this plot on the right, it's about 5 times better than the CX gate. And in this plot, it's about like 4 times, better than the CX, right?
Okay.
Yeah. So all the plots are, so the thing I'm varying in my simulations is kappa, the loss rate. So kappa over Kerr is what I'm varying. And then I get, then I get these plots, and then I look at what fidelities it corresponds, that kappa corresponds to, and then I plot that on the upper x-axis.
I noted, by the way, that your preparation, the preparation of the cat is rather slow compared to like a transbond preparation, right? I mean, 320 nanoseconds is quite rather long, yeah.
Yes, that is the slow part. And there's actually no reason for it to be slow. We didn't want to be too adventurous in the first experiment. But so theoretically, it can be much faster. Theoretically, it should be more like 100 nanoseconds or even smaller, shorter than that. You just need to do a little bit of pulse shaping to get that number right, which we didn't do in the first experiment because we were worried about stark shifts, but now we understand the system better. We know how to do it.
Okay, thank you. Okay, well, I think hopefully there may be other questions in the Slack channel, and Shruti can look at that, but I think we should move on to